Here is the question that we didn't get to finish yesterday in class. We are looking at two blocks connected with a rope over a pulley. We have the mass of the first block, which is um, 5 kilograms. And we have the incline, which is 35 degrees. We also have the coefficient of static friction between M1. M2 is hanging free, so there will be no friction there. And we are supposed to determine the largest mass for M1 before it starts moving. So if there was a large mass of M1 and it caused motion, it would be going in this direction. So we're going to know that static friction would be acting in the opposite direction, which is up the ramp. So first thing we have to do is we have to create a free body diagram. We're going to do it for both masses, and go from there. So mass 1, free body diagram starts something like this. So we have normal force. We have a tension force from the rope. We also have static friction going in that direction, and we have our FG. Now, you can also put a bit of a imprint of the ramp so you can get the exact angle that you need. So this is 35 degrees. We're going to use 35 degrees and the 90 degrees to find this angle here, just by doing minus 35 minus 90, and that turns out to be 65 degrees. That angle will come in useful when we are decomposing that mg force acting down. So if I go ahead and I do that, I will create a right angle triangle like this, and I will get FG X component, and I will get not there. So this is FG X, and this one here is FGY. FGY will be FG sine 55, and FGX will be mg cosine 55 degrees. So now that we've broken the components of the mg force or downward pull, I can create another free body diagram for that same mass. So do that once again. Normal force. I still have tension, and I still have that static friction. The other way now I have FGX acting in that direction, which in this case the and 55 degrees, and the other component is FGY, which is mg degrees. So that is just a new free body diagram with the broken up components of the FG force. We can also do a free body diagram for the mass 2, which will be much simpler. Force of tension acting up. We also have a force of gravity, which is Fg2, acting downwards. So since we have the free body diagrams, we can start looking at the net forces for both of the free body diagrams. The first one, because it's sitting on an inclined plane, we know that the normal and the FGY are acting in opposite directions, so they actually wouldn't be affecting the motion. So what's really affecting the motion is the FGX combination with FS and FT. Because the net force is 0, what we would write is that FGX minus FS minus FT is equal to 0. And then we can isolate our Fs, which would be Fx minus Ft. So that is our net force for the first mass. For the second mass, we have two acting forces. It's Fd and Fg2. So really we can write that F is equal to Fg2 or really equal to N2G because they're acting opposite directions, but they have the same magnitude because the net force is 0. So what we can do now is we can do some substitution. So the Ft that we got from our second free body diagram, we can use in this formula. And our Fgx we have up here. So we can express Fs as m1g cosine 55 minus m2g. So at this point, this is all we can do with this formula, but we do have another formula for Fs. So Fs can be also expressed as mu s times Fn. So we can create another side to this equation. We can make them equal and then maybe solve further for the mass that we're looking for. If you remember from yesterday, if we are looking for the normal force, we are really looking for the opposing force that's in the other direction, which is FGY in this case. So all I'm going to do is I'm going to write as Fs equal 0.25 is mu in this case, and then m1g sine 55. Now that we have two different expressions for Fs, so this one here and this one here, we can make them equal. So let's start by saying Fs is equal to Fs, and then we can just further substitute 0.5 and 1g sine 55 and m1g cosine 55. If you notice that all terms here contain g, so we could factor out g's on the right side, and eventually they would all cancel out, so we can just cancel them out right away. So really what we are left with is 0.25 and 1 sine 55 degrees and 1 sine 55 degrees minus m2. The good thing here is that we have m2 as a variable, which we have, and the other variable is m1, which we are looking for. So all we have to do now is isolate m1 further. So if we move all the m1 terms to the left side, we have 0.5 m1 sine 55 minus m1 cosine 55. And now we can factor out m1, which is 0.25 55 degrees minus cosine 5 degrees equals minus And we can divide both sides by this bracket here, and that will give us M1 isolated. So that is negative M2 over 0.25 sine this 5 degrees. From here on, it's simple substitution. In this case, it's negative 0 for mass, 0.25 sine. You put this in a calculator, you will get something like 13.5 G79. And if you look at significant digits, it should be around 14 kilograms. So this is the maximum mass that M1 can have before it starts moving, and that is it. Another example that I wanted to do yesterday was a pulley system. Let's say we have a pulley, and we have two masses. They are connected by a rope. Let's say this is M1, M2, 10 kilograms, M2 is 20 kilograms. If this was the case, the acceleration would be going in this direction. That would be the positive direction for the M1, and for M2 it would be this direction. And let's say the question asks you to find the acceleration and find the tension force. All right, so whenever we have questions like this with pulleys, we will create two free body diagrams for both masses. So we can do the M1 first. M1. In this case, there are no horizontal forces acting. You only have the vertical ones. So for M1, you have the Ft going up, and you have the Fg. I'll mark it as Fg1, which is M1g in this case, and the acceleration is going this way. And then for M2, it's pretty much the same. So I have a tension force going that way, up. And in this case, it's Fg2 going downwards, and our acceleration would be going in this direction. So all we have to do now is look at net forces, and we're just looking at the y component, I guess. So net force. Net force is mass times acceleration. So m1 is acceleration, or the first one. We can also express net force as a combination of Ft and Fg1. In this case, because our positive direction is up, minus Fg1 or Ft minus M1. And from here, we can actually equate these two expressions. We can equate the M1A and Ft minus M1G and create an expression. So M1A is equal to Ft minus M1G. And now we have an option. Because we're looking for tension force and acceleration, you can isolate one of those variables. It doesn't matter which one. You can always come back and find out the missing variable after. I isolated the acceleration here. So what I got minus g over m1. And this is just for the first mass. Now the second mass, I'm going to do the same thing. So the second mass also has net force of M2A. So I guess we could label them as 2 and this is 1, just to distinguish. In this case, it's the same. We're going to write another formula, relationship between FD and FG2, but because our positive direction is in downward direction, we're going to write it as M2G minus FD. And then do the same thing, equate equal to M2G minus FD. And because I isolated acceleration in the first one, and it's the same acceleration between the two systems, we're going to isolate the acceleration as well. So we'll get that M2G FD over M2. And now that we have two expressions for acceleration, what we can do is just combine them, make the accelerations equal. So and then just substitute. So G over M1 is the same as M2G over M. We have M1, we have M2, we have G. We're looking for FT, so at this point we just have to isolate the FTs. I just decided to cross multiply it. So I'm going to take the M2 and I'm going to multiply it with both terms in this numerator, and I'm going to take the M1 and multiply with both terms in this numerator. What that turns out to be is FT M2 plus, nope, so FT M2 minus M1 M2G, and then same thing on the other, similar thing on the other side, M1 M2G minus FT M1. Now we can move all the FTs to one side, which means that I will combine these two eventually, and I'm going to move the other variables to the other side. This turns out to be FT M2 plus FT M1. That is equal to M2 G plus M1 M2G. You'll notice that these two are identical, so really we have two of them, so we can express that the next line as 2 M1 and G. We just add them. On the left side, we can isolate FT, which leaves us with M2. And now we can just isolate it. 2 M1 G over M2 plus 1. And now we just substitute the values. So we have 2 times 10, 20, 10, all of that over 20 plus 10. That turns out to be 130.667 newtons, or 0.3%. So that gives us the tension force. All we have to do now is take that tension force and substitute it in one of these expressions. It doesn't matter which one. I guess I'll take this one. I'll just rewrite it at the bottom. Acceleration is equal to 2G FT over M2. 20 minus 136 over 20, and that turns out to be 3 meters per second squared, and that is the acceleration. And that is it. So for this question, what we did is we did the two free body diagrams. We looked at the net forces, and it turns out that we have common variables that carry through the boat system. In this case, acceleration and FT. We isolated acceleration in this case, but you can isolate FT and then um, find your acceleration and then find your force of tension. It doesn't matter which order you take. And that is it.